There's no clocking. Oh, there we go. So 3 minutes. Mm-hmm. Oh, Dr. Miguel is not here.
Got one to make the show.
Good, good, good,
I've
good.
been advertising the heck out of it, saying, come see it, it'll change your life.
Yeah, I'm also waiting for my host family to come, but I haven't seen them yet. You know Dai?
No, I do not.
Dai is a senior guy that is the tutor. Oh, Dr. Miguel. He's a tutor of IoT class this quarter.
Oh,
So
okay.
maybe you saw him, but you don't recognize him. Alrighty. 1 minute to go.
We'll try not to get in. There's a pretty magnet here, so we'll try not
Yeah.
to try to
We're
see
gonna be
promises,
jumping
but no
around,
promises.
act like snow leopards.
Yeah, we're gonna do a whole snow leopard demonstration. Full arm. We haven't. We haven't. We get like 4 clickers on this.
Okay. Hey guys, um, when people are doing questions, we don't have a spare mic, so no one can hear the questions. So it's a good idea to repeat what the question was, and that way, it's up to you. I mean, this video is going to be for.
Can I go around the crowd and be like, all right, sir?
Yeah, that would
You
be
can
a
do
nice
whatever
program.
you want, but it's good to at least repeat whatever the question was.
Okay. Sure.
And if you don't, that's fine too.
Yeah. 159.
Babe. Shall we start?
Are we? That's very impressive, Dr. That's doubly impressive. You think I did it? That's great. That's amazing.
Okay, I think we're going to go ahead and get started. If you're here to see computer science, you're in the wrong room. They moved over that way. But hopefully you're here to see electrical and computer engineering. Better. We're going to go ahead and start. The teams will introduce themselves, and we're going to start with team number 7.
All right. Hello, everyone. We are Team ECE 18.7, Project Spotcheck. And so today we are talking about developing a computer vision-based software for identifying individual snow leopards from camera traps photographs. And so here's our team, David Grubb, Ross Hartley, and me, Tim Wing. And so here is the support we are receiving. We have our faculty advisor, Dr. Agnieszka Miguel. She is the chair of the ECE department, and also she is a specialist in image processing field. We have our project liaison over there, Rana Barashid-Smith. She is a project manager for Panthera program. We have our technical advisor and Rich Bankhead and Matt Yoso. They are expert in Python programming. And so here's a little bit about Panthera, our sponsor. So Panthera is founded in 2006, and it is it is a nonprofit organization, and it's devoted exclusively to to the conservation of more than 40 different wildcat species around the world. And one of their program is the snow leopard program. So why snow leopard? Because it is one of the wildcat species that is currently classified as vulnerable in the red list of threatened species. Snow leopard is also a very elusive and secretive species. Its current population is estimated around 4,500 to 10,000, and that's spread across 12 different countries in Southeast Asia. So you can imagine that that is a very, very challenging task to survey the exact population. So the snow leopard program has been conducting camera trap studies. So each study will be around 40 to 50 different camera traps. You can see some examples of the camera traps over here. So these cameras are motion activated. So every time that the camera sends some motion, they're gonna take a series of images. So for example, like this. And so oftentimes it will be a series of images of a snow leopard, or sometimes there will be maybe of other species, but they will be sorted out so that at the end of each study, it will contain only images of snow leopards. And so these images of snow leopard will be identified manually by biologists. And so each image takes about 30 minutes for biologists to manually identify the identity of the snow leopard. And so as a result, at the end of the study, it will take like hundreds of hours to finish identifying the whole image set. And so Panthera has been collaborating with research teams at Seattle University to develop a software that's capable of automating this task. The first team to start with the software was ECE 17.7 from last year. They started with Hotspotter, software that was developed by Sean Kroll, a research graduate from RPI. And so originally the software worked on zebras, but ECE 17.7 adapted the software so that it works with snow leopards. They got the identification accuracy to 60% or above. They implemented the automated chipping process. The performance they got was roughly around 1 minute per image. And final implementation from ECE 17.7 was the streamlined graphical user interface. And so here's the overviews of Hotspotter from 17.7.
All right, thank you, Tim. So 17.7 implemented these three algorithms: auto chipping, auto querying, and clustering. So the first of them is called auto chipping. What auto chipping does is it looks through these templates. You can see one right here. Those are produced by Dr. Miguel's research team. What it does is it goes through and it finds 3 large rectangles within each template, and then it correlates them to, correlates them to the real image right here. And then it pulls them out, so we have those 3 right there. The reason for this is we don't want to process the entire image, just small portions that Hotspotter can do its work on. So the next step in the process is auto querying. So what auto querying does is it takes those chips we mentioned earlier. Here are 2 in those 2 images. And it processes them and comes up with similarity scores between them. So you can see right here, all those little red circles are areas in the image that Hotspotter has identified as being of particular interest. And you can see right here, those 2 spots were highly matched by auto querying. And in fact, these 2 pictures are of the same snow leopard. The last part of the process is called clustering. What clustering does is it compares those scores that are generated by auto querying into identifiable cats. So you can see right here, we have 3 images, and then they go into auto chipping. We pull out these 9 chips, and then from there we get these score tables. So you can see the one on the left has a lot of high scores kind of spread all around, but the one on the right is all 0s and 1s, with the main row being right here. And so we have right here is a visualization of those scores. So a score of 0 is a no match, so no match at all, whereas a score of 1 is a high 100% match. So you can see, rather than having the scores all spread out, clustering has identified one solid bar of 1 cat. So now we're going to talk about the improvements that we've made. So as part of our project, we wanted to focus on 4 main parts. We wanted to give Hotspotter a more intuitive workflow. We wanted to increase the identification accuracy. We wanted to improve the program runtime by reducing runtime. And we also wanted to improve stability and usability of the software, which Tim is going to talk about now.
Thanks, Ross. So to talk about the more intuitive workflow, the first implementation we made for Hotspotter this year is to have Hotspotter always load the default settings on startup rather than from last version. So every time that you load Hotspotter up, and then no matter which database you start Hotspotter with, it always loads the default settings so that the result calculated by Hotspotter are going to be consistent rather than previously Hotspotter will load the settings based on the last run settings. And then another implementation we made to improve the workflow is the automatically save progress. So previously, every time that a user run Hotspotter, they will have to click the Save Database button at the end of each process. But from now on, Hotspotter does the Save Database automatically, so user doesn't have to care about that. And then another feature to improve the workflow is that Hotspotter now allows user to rerun auto-chipping process without corrupting or conflict with the previously calculated data, because previously auto-chip, if it is rerun, it's just going to append the new calculated data to the old data, which will result in incorrect recognition result. From now on, auto-chipping will erase everything that was calculated previously and start out fresh. And then to talk about increased performance, I'll hand it to Dave.
So when we did our performance analysis initially, one of the major things we noticed was it was the auto-chipping module by far that was taking the most time. It would be around a minute per image with maybe a couple seconds in the other modules. So this is one of the ones that we targeted to increase performance. We went ahead and enabled it for multi-threading. And so as you can see, it now is chipping in parallel. You can see a little output from the console. This gave us over a 70% reduction in runtime. So we're down from a minute to just over 18 seconds on average per picture. We did find in our testing that using all the cores on any given machine was a little too intense and it wasn't very responsive to the user. So we did end up dialing it back to N-2 cores. And that is the 70% number is with N-2.
All right, thanks, Dave. So for improvement in recognition accuracy, one of the new features we experimented with was the auto-querying by number of cats and flanks. So the idea is that Hotspotter has been comparing images of snow leopards without knowing that the size. So it has been comparing images of snow leopard no matter which side of the snow leopard is contained in images. So this new prototype, as you can see right here, what it does is that it separated a database of snow leopard images into set of images of snow leopard with the same side. So let's say it's gonna separate a database of snow leopard images into left side, right side, front and back, like you can see here. And so thanks to this module, the other processes of Hotspotter are gonna increase in the recognition accuracy. So as you can see here from this table, across different clustering algorithm, when we run Hotspotter with classified by flank, it's gonna increase the recognition accuracy on average by 10%. And so about clustering.
All right, so to start off, we're going to talk about the clustering method that was implemented last year by ECE 17.7. It's called Markov clustering. What it does is it takes the scores between each chip and it will increase high scores and decrease low scores until you have only 100% matches and only 0% matches. So in our experimentation with that module, we identified one parameter in particular as providing the most gains in accuracy. That's the inflation factor. So what the inflation factor does is it kind of affects how distant two clusters are allowed to be before they're combined. So you can see right here, these two images are of the same data set. You can kind of tell if you imagine rotating them in your head. You can see with the lower inflation factor, it only identified 2 clusters, whereas with the higher inflation factor with smaller, more granular clusters, it counted 5. And we tested this data set for accuracy, and we found that the high inflation Markov is actually more correct. So with this new parameter for Markov clustering, we managed to increase accuracy by an additional 10% over last year's team. We also, as part of our work with clustering, wanted to experiment with other clustering methods. So these are 2 of our major candidates. They're called single and group linkage. They work under the concept of every chip starts out as its own individual cluster, and then the two most similar clusters are repeatedly combined until you end up with one big cluster up here. So you can see all these little vertical lines are chips, and every time they meet, that becomes a new cluster. So as it goes up, the two clusters being combined are less and less similar. The difference between these two is based on how it calculates how similar two clusters are. So the different colors each represent one cluster that was found. What we found issue with this algorithm was that we have no good way of calculating when to stop. So if left unattended, it will go all the way to one cluster, and we don't want that. We want to be able to identify the individual cats. So we have recommended for next year's team that they do more research on that stopping point, and if they can find one that's flexible enough to provide accuracy as well as flexibility across a bunch of different data sets for different cats, then we think that these two clustering algorithms are definitely strong candidates for improving accuracy further. All right, and now Dave is going to talk about improved stability and usability.
So one of the major usage scenarios or requirements we had from Panthera was it can run on a Windows laptop that a biologist has out in the field. When we first came to the project, it was being developed and tested on Linux, so one of our early goals was to port it over to Windows. So we ported over to Windows, did all our development on Windows from a pretty early on phase, and actually, I think as of late winter, had Panthera beta testing it on Windows as well. You can see kind of an image here of what the workflow would look like. The hotspotter in the upper left, console upper right, and then here on the bottom you can see a picture of an image and its associate chips. So other things we did to improve the workflow was kind of message pop-ups for the users. This saves a little bit of time. Historically, there was nothing to protect a user from redoing the same work by clicking the same button again. Let's say you run auto chipping and it takes 3 hours. If someone didn't know it had been run, they could click it again and reduplicate all that effort. So now it kind of does a check for that, throws up an error message or at least an information message saying, hey, this has been done. If you want to do it, you can change the settings. Similar thing here for each phase of Hotspotter. Now when it's complete, you get a little pop-up that lets you know it's time to move on. In addition, the data wasn't refreshed automatically, so after you'd run auto chipping or clustering or whatnot, it would store the information in a table, and then after you went ahead and saved it, exited out, and reopened it, you'd see it refresh with this information. So from a usability standpoint, we made this real time. So right after it's done, it's going to go ahead and update if you have any new information or identified cats. Another big request from Panthera was to sort the images into folders after they've been identified. So if you have 300 images and it's identified 3 or 4 unique cats in them, it'll be really easy for the biologist to have it sorted for them. So we have a button now that does that. As you can take a look, you'll have like cat 1, cat 2, cat 3 in their own folders. If you had any images of cats that aren't recognized, or it's not sure, maybe it's cat 2, maybe it's cat 3, it'll put it in an unknown folder so the biologist can review it manually. So another kind of quick high-level review of our results. This is kind of what we achieved at a high level. The big takeaways here, again, is the 70% reduction in runtime and the 10% increase in accuracy. And that's not even counting the proposed future work change of sorting by flanks, which would add another 10% on top of that. And to cover our budget, we're a software-only team, so it's pretty low, $140 for parking passes. That's about it. And that concludes our presentation. Any questions? So I'm going to let Ross take that.
So it's electrical and computer engineering, pretty obviously. This is electrical and computer. So it depends on what clustering method you're using. So Markov is a graph clustering algorithm, so that's more of the mathy side. So a graph is it's a data set where you have vertices connected by edges. And so it kind of removes edges on weak connections and makes them stronger on stronger connections, but the linkage clustering is more statistical based. So there's a little bit more math involved in that one compared to the Markov clustering algorithm.
So you mentioned that it takes a human about 30 minutes to annotate a single image, which I think suggests that it's a really hard problem and everything. And I'm wondering if you could compare the performance of your system to human performance, or like inter-annotator agreement.
Certainly, around accuracy, humans still far more accurate, at least having a trained biologist do it. to test our accuracy, we get truth tables from them that say which leopard is what, and they're like literally comparing spot patterns side by side. Ours is up to, well, we had 96% on some databases, but on average it's about 70%. So that's a pretty big difference. And then time-wise, again, like 18 seconds roughly per image for us versus up to 30 for human.
When you mentioned flank, the left, right, rear, was that determined by the image sensor, or was that a human did that?
So that's actually not been done today. That's our recommended future work. We did a proof of concept and some kind of GUI work to see what it would be like, and then manually separated them out and ran to see what the results would be like. But as it would be today, if we were to implement it really quickly, it'd be a human checkboxing if it's left or right. But it certainly could be done by machine learning. So our recommendation for next
More
year
head
is,
and tail.
yeah, exactly. Yeah.
Sorry. Are the spots on leopard symmetrical? Same on left, same on right?
No, that's why the separating the flanks helps so much. Is like left, right, and dorsal all different. So there's no guarantee you're going to see the same pattern one side or the other.
Any more questions? Okay, thank you very much.
Like exactly 15 minutes. I think we're like 14:45 or something.
Hey guys, I didn't know you were that fast.
Yeah.
Stay free.
I'll say it once.
Great job. Good job. You guys did a good job.
Good job, you guys. Good job.
Oh,
Did I need- there's no more.
yeah, it's here. It's right here.
One is enough. One is enough. I was gonna use two, but one is enough. It's alright. Yeah, it's okay. I'll just use the link. I'm good. I'm greedy, I think.
Wait. Oh, what?
What are you doing?
Putting it on the big screen? What the? Oh, that's so weird. This computer's like backwards. There we go.
So our next two presentations are tightly linked. No one will be allowed to leave. Otherwise, you won't understand what's going on. You guys about ready?
Yes, sir. All right, hello everyone. We are team ECE 18.4. My name is Jack Nelson. These are my teammates.
My name is Ty Hewitt.
My name's Tim Lopresto.
My name is Yahya Aliami.
So for our project, we did the CWC, which is the Collegiate Wind Competition, which is a wind turbine competition hosted by the Department of Energy every 2 years. This year is in Chicago, May 8th to 10th. Seattle University applied for this competition, was accepted along with 11 other teams to build a turbine, which is the test turbine, and then a theoretical design, which is the market turbine, and then a siting challenge. So for our presentation, we will be focusing on the test turbine and specifically the electrical side. Our team sponsor was Seattle University. We got support from the Seattle U Student Government and DNVGL, and our faculty advisor is Kevin Lieberger. And I'll send it over to Yahya.
All right. There were some requirements and specifications set by the CWC for all team to follow before, prior to their design of the wind turbine. The wind turbine has to fit in a 45 by 45 by 45 centimeter box. It has to operate in islanded mode, and that means it has to output power without getting power in. In other words, we call it off-grid operation. It has to stand or withstand high wind speeds up to 20 meters per second. All of the electronics has to be fit in one enclosure box for safety. The wind turbine also has to go through different 5 tasks. These tasks are designed by the CWC to represent the actual capabilities of full wind turbine out there in the real world problem. Next slide. Thank you. Okay, our approach was a straightforward approach. We decided to go with 3 plates, horizontal axis. And remember, if you're gonna ever design a wind turbine, please control it. This is the tip. This is your tip of the day. And there's 3 ways of control wind turbines in general. Yaw, there's either passive or active yaw, and yaw means the rotation of the whole wind turbine around the vertical axis. Also, wind turbines are controlled by either fixed pitch or active pitch, and the pitch is the angle of the blades. Lastly, which is the more important method to control wind turbines, is the generator current control. As you can see in here, we decided to go with passive, yaw, fixed pitch, and as I mentioned, the current, the generator current control. Next, please. Okay, this is the 5 tasks required by the CWC. The first one, the current wind speed. The goal of this task is to decide or to test the turbine to see what is the minimum current wind speed. And when we say current wind speed, that means at what wind speed the turbine was able to produce positive current. The wind speed in this task varies between 2.5 to 5 meter per second. The second task is power curve performance task, where the turbine is going to be tested over a region of wind speeds going from 5 meter per second to 11 meter per second, which is our rated power. And the turbine has to maximize its output power at each interval of the wind speeds. As you can see in here, this blue curve is the actual power curve. And we have to achieve a stable power curve, as you could see in here in this region. The third task is the control of output power and control of the rotor speed. The goal here is to obtain or control the power, the output power, and the rotor speed obtained in the previous task. However, the speed right now is going from 12 meter per second to 20 meter per second, which is really high. And the goal is to obtain this region, which is our rated power curve. One might ask, why do we need to control a turbine? Why not let it run and produce more power? One simple answer could be overprotection for our component, generator, and control system. The fourth task is the safety task, and the goal here is to demonstrate a safe stop of the wind turbine. There's 2 methods of doing that, either by manually, industrial, like emergency stop, looks like something like that. When the button is pushed, the wind turbine has to stop safely. The other method is by load disconnect. When the load is disconnected from the turbine, the turbine has to stop safely. The last one, the durability task. The goal here is to maintain a constant 5-volt output under variable wind speed, variable yaw, and also variable load. The team is also asked to use the energy storage element provided by the CWC judges in case of low wind speeds.
Which one is that? Okay, now we'll start talking about the electrical system as well as the control analysis. This is kind of your basic functional block diagram of a wind turbine. The goal here is just essentially to convert the mechanical power captured by the wind and turn into electrical power for the grid. One thing to note here, in our project, it is a multidisciplinary project, so the electrical teams and the mechanical teams are very closely coupled in this design process. Looking at this diagram, the faster essentially the rotor speed, the more power is produced. Essentially, we can't change the wind speed, but we can change the rotor speed and the generator speed. So for our control system and electrical system, we want to essentially change the generator speed by controlling the generator current. And this is kind of the process that we take with our control systems as well as our electrical system on how we control that rotor speed. Just to kind of go on to kind of dive into the actual electrical system, so in order to match the rotor speed to the generator speed, we did implement a gear reduction ratio of 5.5 to 1. So then we have our 3-phase generator that, and we take that AC current, go through a full bridge rectifier into DC, and then that DC current goes in DC-DC converter, and outputs a constant 5 volts to the load. We have 3 major kind of components to our system: the load, the dump load, and the storage element device. Each one has an N-channel power MOSFET, essentially a switch that's controlled by a PWM signal sent by the microcontroller. Now, as mentioned before, we are using generator current control to control the rotor speed. So that switch will control the current going through the load, in turn control the rotor speed. Now, the dump load essentially is to, when we want to shut down the turbine, we will dissipate all the power through that dump load to essentially safely apply a brake to the rotor. The storage element device is there needed for when the load demands more power than the turbine is actually, or the wind is actually available.
All right, so for the control side of things, we designed it to operate the turbine in 3 different regions of wind speed based on measured rotational speed, as shown on the graph. So in region A, where the wind speeds are low, our turbine will be placed in an idle state, meaning that no current will be commanded in order to reduce the starting torque, allowing the turbine to start more easily. Now in region B, where the wind speed are high enough for the turbine to start generating powers, a small amount of current will be commanded through a low duty cycle of pulse width modulation signal. This is mainly for the cut-in wind speed test. And in region C, where the wind speeds are strong, our turbine will be operated as a fixed speed machine by using the proportional integral controller strategy to vary the duty cycle of the pulse width modulation signal. Now, in most cases, our turbine will be operated as a fixed speed machine. The reason why we want to regulate the speed is because we want to keep the power output relatively constant as the wind speed increases above the rated wind speed and the aerodynamic efficiency begin to decrease. Now we designed our turbine to have a rated wind speed of 11 meters per second. However, for the control, we designed it to start regulating the speed at around 6 to 7 meters per second wind speed. This is to ensure that sufficient amount of current is commanded to charge the storage element when the turbine is experiencing wind speed between 6 meters per second all the way to the rated wind speed of 11 meters per second. And here is just a basic diagram showing how the decisions are made in the program. To ensure a quick and safe shutdown, the condition of the shutdown are checked at the beginning of the loop. If you recall, the condition for the shutdowns are when the manual switch button has been pressed or when the load has been disconnected. If a shutdown is required, then the program will command current to the dump load to dissipate power and apply a brake to the turbine. If a shutdown is not required, then the program will operate the turbine based on rotational speed in each wind speed regions.
Okay, now we will talk about the wind tunnel testing. The first one is at Seattle University. So Seattle University doesn't have a large enough wind tunnel to essentially house the size test turbine that we have. So one was built, and as you can see on your right, it's made out of 4 leaf blowers. And these leaf blowers have 3 settings: low, medium, and high. We've run into some problems, especially non-uniform flow, but all to say that most of the iterations were done using this wind tunnel, and it kind of gave us a sense and validated some of the mechanical and electrical systems that we have. Now, because of this, we wanted a more sophisticated wind tunnel, so we did, for one day, rent out the University of Washington's Kirsten wind tunnel. It was fairly expensive, and so yeah, we could only have it for one day. But through this, we were able to kind of validate some of the CWC tasks, along with obtaining a power curve of our test turbine.
All right, now we will be moving on to the result. But before that, I would like to inform you all that we will be not covering all the results. The additional results, such as the one from the competition, will be covered by the mechanical engineering team 18.2 in their presentation. So stick around. All right. So here is the result from our one-day testing at the UW wind tunnel. This is a power curve generated by our turbine using our design electrical system and control methods. As you can see, by regulating the speed, we were able to keep the power relatively constant throughout here at a high wind. But as you may have noticed, our cut-in wind speed was a lot higher than we had hoped. This was mainly due to the starting torque of our generators, which affected the cut-in of our turbine more than we expected. By this time, after the UW testing, it was too late for us to select a new generators, so we decided to try and reduce the cut-in wind speed of our turbine through a mechanical approach, which will be covered by the mechanical engineering team in their presentations. And here is one of the results that we got from testing at the SU wind tunnel. This is a graph showing the generator speed being regulated by our controller. In this case, the desired speed was set to 500, as indicated by the red line. And as the measured generator speed increases above the red line, our controller started to regulate the speed to the desired speed. Now, we were unable to verify if the speed we could regulate the speed as well as power in all wind speeds, since, as mentioned by Tim, our leaf blower wind tunnel only have 3 settings: low, medium, and high, and this was generated at the highest setting. However, we were able to use our wind tunnel to test our safety mechanism, the shutdown from our control. As you can see, we were able to shut down the turbine within 10 seconds under both conditions stated in the safety test. Additionally, we were also able to charge the storage elements. However, our turbine could only produce about 3 to 5 watts in our wind tunnel at the higher settings. So the charging of the storage element was very slow, which made it difficult for us to do an accurate testing for the durability test.
Thanks, Ty. So I'll quickly walk you through our budget analysis. We had 2 major areas of spending, the power electronics and the generators. We spent about 57% on power electronics, about 43% on the generators. We went through about 3 different iterations of generators and then bought a backup of the final generator that we used in competition. Power electronics, that's sort of everything the diagram Tim was talking about, the rectifier, the DC to DC converters, all the wires, resistors, and then the box we house that in. We came in about $436 under budget, which is great. And yeah, that is our budget. And again, mechanical team, we couldn't have done without them. They're about to present our results from the competition, but if you have any questions on the electrical systems or anything we just presented, we'll take them at this time. Thank you.
Any questions?
Do you guys have any thoughts about redundant controls that might be necessary on the full-scale turbine for like, loss of load shutdown and stuff?
I'm not familiar with the redundant control.
No, I was just curious if that was something that might be required on a full-scale turbine, or if you had any.
Oh yeah, for a full-scale turbine, it would be most turbines have an active pitch as opposed to like a fixed pitch that we did have, and it also have a active yaw. So they be controlling both the blade angle as well as the rotation of the turbine.
Is what you guys did here the same as big turbines we see over in East Washington? Except bigger?
A little smaller.
A lot smaller.
Of course not. It's not gonna be the same. You can't just take one, like a tower big, and bring it to 45 centimeters box and say it's the same. It's a representative of it. It's has the same way, the same methods of control, but of course it's not exactly the same. Like even aerodynamics, like up in the sky, it's not. It's different from for leaf blowers. So. Matthew.
You said this is a competition. So what was the difference between your project and your 10 other competitors in design or testing?
All of the other competitors were subjected to all the same tasks and requirements. So all the other ones, were building and testing their own turbine that had to be required to be subjected to the same tasks. Some of the competitors they had been doing this for a while, actually. This is our first year. So some of the competitors had some sophisticated turbines, which was really educational and very interesting to watch. There were some great teams, but they had been competing for for the last 4 years. They've been working on their design. So yeah, this was a very educational process for us, for sure.
Which specific type of generator did you use? You said it was a three-phase induction.
It's a permanent magnet generator. And I think Jack briefly mentioned it. In the beginning, we started off using copter motors and just kind of ran them backwards to act as a generator. However, the rotational speeds, we weren't getting them to spin fast enough to be able to output the amount of voltage that we needed. At least with our testing, we weren't able to. And so this is actually a small-scale wind turbine generator, a permanent magnet generator. And so it's a fairly high rating. Like the power rating is 100 watts, and the rated voltage is 24 volts at a rated RPM of 700 RPMs. So it is large and bulky for sure, but for just getting it done and what we needed at the time we made it work.
Also, just want to point out that most generators are not designed for this type of scale, small scale wind turbines, so it's very difficult to try and find the right generators. Most teams actually design their own generators. So if we have a lot more time, we would have designed our own generator for this. Yep.
Yeah. I believe 24.
We're going to have to cut it off at this point. Thank you very much. We'll move on to the next one.
Is this ours?
Yeah, or
Kyle's. There you go. Killed it. Okay, you have to plug it in, Yaya. Really?
I don't think we have a place to plug in that
Really?
Yeah, you're using all sorts of.
Oh, you have all.
I guess the only thing is if you're willing to do without a mouse, you can pull the mouse off and try plugging it in the back.
Yeah, I think we can do that.
Try that?
We're the last team.
Oh, wait.
Yeah.
So, at the end of our presentations, after question and answer, we have some trophies to give to our advisors. Is it possible to announce that it's not the end yet? At the end of the question and answer?
Okay.
Yeah. You get these first, actually. Okay, where's the pointer? This is the pointer? Yes. And this is for the slides? Yeah. I'm guessing this is forward? Yeah.
We also have this one too.
Hello everyone. Welcome to the second Collegiate Wind Competition presentation. My name is Kyle. My teammates are AJ, Barbara, and Alicia, and we are Mechanical Engineering Team 18.2. Also, our advisor is Dr. Matthew Shields. So in the last presentation, the EE team did an excellent job explaining what the competition was and the components that they worked on. For this presentation, we will talk about the components we worked on, which included the blades, the hub, our pulley system, our nacelle, our yaw system, which is a fin and a yaw bearing, our tower, and our base, and as well as the results of the actual competition. So Yaya also did a good job of explaining a lot of the rules and requirements of the competition. The main ones that impacted our team is that the turbine has to fit into a 45 by 45 by 45 centimeter box. This governs the maximum power that our turbine can actually capture. We also have to have our nacelle and our fin fit into a 45, be less than 45 centimeters, which impacts how our yaw system will function. We also have to withstand winds up to 20 meters per second, which deals with our safety factors on our turbine design. And also we have to yaw up to 180 degrees per second for a total of 720 degrees, which again goes back to that yaw system. So from those 5 tasks that Yaya outlined already, the impacts that has on our team is, one, we need to cut in at the lowest possible wind speed. This is when we start actually collecting points for the competition. We also want to maximize our power or maximize our efficiency at 7 and 8 meters per second. This is because during that power performance task, each wind speed has a different weight factor, and those 2 wind speeds have the highest weighting. Also, from the EE team, we know that we want to have our generator spinning at 700 RPMs. So this is the first year that Seattle University has entered this competition. So because of that, we wanted to have something that we could take to the competition we were confident would work. Once we had a base model that we were confident on, we would make these small iterative improvements on that design. And we want to do a lot of testing to ensure that those improvements are in fact improvements, as well as build confidence in our computer modeling. And with that simple design, we decided to go with, like Yaya said, a fixed pitch control and a passive yaw control. And again, the yaw is what allows our turbine to rotate when we have varying wind directions. And we also wanted to have a large safety factors. We're dealing with a lot of 3D printed parts, which means that some of our stress analyses were not exactly, FEA doesn't really apply to some of these factors. And also our wind tunnel can't actually go up to 20 meters per second. So we wanted to be confident that our turbine wouldn't break while at the competition. So to actually talk about the actual design of all of the components, we're going to start with our nacelle, which houses our pulley system and our generator. And like the EE team mentioned, our generator is fairly large. It's about 6 inches in diameter. So to try to increase the efficiency of our design, we went with a triangular shaped, which you can see in kind of version 3, where we have 1.5 inches wide at the front and 6 inches in the rear. You can also see we have a pulley system on this. That's because the blades want to rotate at a much higher speed than the generator. So this also allowed us to gear up the torque of the blades, which would help with our cut-in wind speed. We also went with a pulley system versus gears for several reasons. One, these are much cheaper. We can actually manufacture them ourselves and get a little bit more customized gear ratios. We can also quickly test different designs. We wanted to experiment with what pulley ratio we went with and which would be the most effective. And this also gave us a little higher tolerance when actually manufacturing our nacelle to make it a little easier. With those benefits, we also had some drawbacks. We had some issues with the belt slipping and breaking, and while at the competition, we actually had issues where when we tried to regulate the rotor speed, the belt would actually walk off of the pulleys, which was then our turbine would lose control. And we also have just some general transmission losses through this pulley system, but we were okay with taking those based off the advantages we got. So talking about our yaw system, like I previously mentioned, we went with a passive yaw, so we have a large fin on the rear and a bearing that we made in-house to try and reduce the friction of that yaw motion. We also, like I previously mentioned, we have a fixed pitch control. So we originally had a 3D printed hub. However, we were having some issues with the hub breaking at the root where the blades actually connected to the hub. So we decided to manufacture one out of aluminum, which we were much more confident going into the competition that this would hold up to 20 meters per second.
So now moving on to the blade design. So our blade design started by going off into doing research on blades and how they work. And once we gathered that information, we would put them into QBlade, which is a publicly available aerodynamic design software. And we put in information such as different airfoils, and we were able to mess with the different blade geometries. We were also able to put in different wind regime properties. Once we put all of that information into QBlade, through QBlade we ran through some simulations and gathered information such as a power curve and a performance curve. We then compared all of those graphs and looking at different blades, and the ones that were most promising were the ones that would get 3D printed using stereolithography or SLA printing processes. And then we would go ahead and test those at the Seattle University wind tunnel, and gathering data and analyzing those results, we would go back and change anything that needed to be changed, and the process would continue. So as mentioned, the two curves that we would look at on Q-Blade were the performance curve and the power curve. So just to define those two, the performance curve is the ratio between the power output and the wind power into the turbine. And power output could either be purely aerodynamic or purely electrical power output, which we would be differentiating between the two throughout the whole presentation. TSR is the tip speed ratio, and that is the ratio between the wind speed that's going into the turbine and the wind speed that the tip of the blade sees. This curve is really important because it's non-dimensionalized, which means that we can use it to compare different blades and figure out which one is going to perform better, since it gives us the efficiency of the ability of the blades to extract power. And then we have our power curve, which gives us our maximum power output at different wind speeds, and also allows us to see our cut-in wind speed as previously talked about by the ECE team. Here we can see our different blade designs that our team went through. These 5 different blades were actually 3D printed and tested, and the blade that we ended up taking to the competition was blade 5, which used the airfoil SG6040 with a thickness to chord ratio of 18.5 and a twist of 30 degrees at the root and at the tip closer to 0. We also ended up making our airfoil of the root closer to the hub, and that was to increase the lift during low wind speeds for our cut-in wind speed. So here are our computational analysis from Q-Blade based on the blade that we took to the competition, blade 5. And as we can see here, we have our expected power output at 11 meters per second to be about 24 watts, excuse me. And that is, we fixed the rotational speed of the blades of the rotor at 1300 RPMs. And then we also have our coefficient of power and our tip speed ratio curve. And we can see here that we have a tip speed ratio of about 4 and a coefficient of power of about 0.3, which is what would be expected of a small wind turbine. This curve is purely aerodynamic, and that means that it's ignoring the mechanical and electrical losses. And it's important because it gives us the upper bound of the expected performance of these blades.
Awesome, so that wraps up the design portion of our presentation, and we're going to finish with testing results. You can see in the top left picture, the electric team mentioned it in their presentation, but we had to fabricate our own wind tunnel at SU because it wouldn't fit, our current wind tunnel doesn't fit competition specifications. So it's made out of 4 leaf blowers. We acknowledge it's not the perfect wind tunnel, but we're using it for comparative testing between design iterations, so it was good for that purpose. And we also went to the University of Washington's Kirsten wind tunnel. It's really high quality and representative of competition test conditions, and it was really expensive, so we could only budget 1 day of testing. So getting into the test results, major test results, the power curve is the same one from the electrical presentation. We just want to highlight that comparing to the computational results of Q-Blade, it's a lot less, but that's expected because Q-Blade is a blade element momentum solver, so it ignores a lot of mechanical and electrical losses, system losses. And one positive thing to note is that it shows signs of stall regulation at about 10 to 11 meters per second, and that fits in with our control scheme as well. The performance curve is made up of 2 trials at UW's wind tunnel at 8 and 11 meters per second, and 1 at SU at an average wind speed of 11 meters per second. As expected, the computational results serve as the upper bound for the experimental performance curves. But what wasn't expected was the discrepancy between SU and UW results. Moving on to identified problems. At UW, it wasn't the final system we tested, so we had an overall lower expected power output, and that kind of affected our power electronics and control schemes at the wind tunnel. At SU, the 4 leaf blowers kind of introduced a lot of uncertainty in the flow, so non-uniform, unsteady, and unknown mixing of the flow, and that affected our average velocity approximation. So in general, that's a cross-section of the test, the Seattle U wind tunnel. The highest velocity is seen right in front of the leaf blowers, and it kind of dies down in the middle. As a first approximation for the average velocity seen by the wind turbine, we just average the highest and lowest wind speeds. And just to remind you guys, the purpose is comparative testing for the wind tunnel. That was the original thought process. So we're more concerned about is design A better than design B rather than specific wind velocities. So averaging two, we get 11 meters per second. Kind of zooming in on the discrepancy between performance curves. Ideally, we expect coincident curves because everything is non-dimensionalized. But there's obviously a difference. And we kind of went back to the average velocity assumptions we previously made. We're concluding that it must be less than 11 meters per second. So kind of by varying the average velocity seen by the wind turbine in our non-dimensionalization, we found that at a wind speed of 7.25 meters per second, all three curves show much more agreement. And in general, the SU wind tunnel is significantly underperforming what we're expecting. We're expecting 11, we're seeing 7. And that affected the direction of our design process as well. We oversized the generator, implemented gears, selected some power electronic components that aren't as efficient in the wind actually being seen by the turbine.
So moving on to how we actually did at the competition. On the right, you can see a video of our wind turbine cutting in at about 8 meters per second. That may or may not be playing automatically. Okay, you won't see a video of our wind turbine cutting at 8 meters per second. So our wind turbine was able to cut in at 8 meters per second, and then it started producing actually more power than we expected, but that power was fluctuating greatly, so we didn't score quite as many points as we had hoped on that. And then during the control of rated power and rotor speed task, same thing kept happening. We did manage to score a couple of points on the control of rotor speed, but the belt on our pulley ended up breaking, so we were unable to continue on to the safety shutdown and the durability tasks. So just to give you an idea of what our actual power output was at the competition, on the left we have the graph that the competition was outputting, and that shows kind of the different power spikes that we were having, and then they kind of ended up maximizing out around 32 watts. And on the right is a graph comparing the maximum absorbed power at the competition in blue to the expected aerodynamic power output from Q-Blade that we presented earlier. And some of the main differences to note are that our cut and wind speed was higher than expected. And part of that was because Q-Blade only accounts for aerodynamic performance, and as we mentioned, we have an actual system here, so things like the starting torque of the generator and the fact that the controller had to be powered off of the turbine itself kind of increased the cut and wind speed. We actually ended up producing more power than we expected, and part of that was because we had expected the controller to kick in and regulate the rotor speed down to 1300 RPM. It didn't do that. And one thing that we actually noticed from this is that regulating a higher RPM actually would increase turbine performance. And then, like I said, our power ended up maximizing out around 32 watts, which was just kind of the maximum of the generator. So how did we do at the competition? Out of 12 teams, once again, we were one of 4 new teams. We actually placed 5th overall. We placed 3rd in the technical design, 8th in the turbine testing, and then as a shout out to the business and siting teams that were there at the competition and did a bunch of work on that, business team got 3rd place and siting team came in 8th. And so in conclusion, we did pretty well as a first-year team. We have a good turbine to pass off to hopefully a team that will compete in another 2 years. So some of the main takeaways that we'd like to leave, mostly for that future team, is that the testing environment is really important. So any improvements that they can make to the wind tunnel at SU would be great. And also if they can gain access to more uniform wind tunnel, for instance, there is a smaller one at UW that might be available. Especially more times and earlier on in the design process, the better. Another thing, like the electrical team brought up, and AJ brought up, is that we sized the generator based on what we thought that we were measuring at SU, and so we think that we oversized the generator, so especially on the mechanical side, any generator that could be smaller, lighter, or have lower starting torque would be great, so maybe go back to looking at those quadcopter motors. And then finally, the transmission. We had a lot of problems with the pulleys. Ideally, the team would be able to use direct drive. If that's not possible, we personally recommend going with metal gears. So with that, are there any questions on the mechanical components or the competition results for either team?
Any questions? How much did those rotten huskies charge you for their weight?
So part of our budget, we had the $1,500 from the project center, but we also had a $20,000 grant from the Department of Energy, and most of that went to travel expenses, but that's what that day of testing came out of.
So for your 5-blade iterations, you had one airfoil for each one. Did you have the same airfoil at each of the stations along the blade?
Yes, yes. We stuck with one airfoil. The NACA 5230 that you saw, that one was thicker, and that was just to experiment to see if it would work. We didn't get the expected results, so we went to a thinner airfoil, which is the SG6040, and we used that one specifically because of its structural integrity, as well as its ability to operate in low Reynolds numbers, and it's also used in small-scale wind turbines.
At the competition, were you able to observe your competitors and glean from them some improvements that the school could do in 2 years from them? Like Espinosa?
Well, absolutely. There was lots of teams, lots of different kind of designs. Many teams also actually went with an active pitch system. In particular, one team chose to use an active pitch system with individual servo motors for each blade, which from talking to that team, they really did not like. And so if we did go with a fixed pitch or an active pitch, definitely wouldn't do something like that. Also, a lot of the other teams did use quadcopter motors. So that's kind of why we want to go back and try and reevaluate that, because that might be more effective.
There were also some really cool ones, like one of the coolest designs that we saw was a team that had active pitch blades, so they were actually able to turn them out of the wind. Also had one-way bearings, so for the safety stop task, that was a really cool way to do it mechanically versus our system was set up to do it electrically. There were some pretty cool ideas out there.
And then in terms of the blades, we saw a lot of blades that looked similar to the ones that we took, but they were a lot thinner, which is something that we were sort of afraid to try due to just like the structural analysis that we did on them. So I would say exploring thinner blades in the future.